Alrighty. Austin, first, I want to apologize to you for missing our meeting earlier. I literally just got home from the vet's office. The Entergy appointment ran a little bit long, so I apologize for that. I'll try to meet with you as soon as I can.
Yes, sir, no problem.
All right. Excuse me. Today, we are going to be talking about the total response of first order circuits. And this is slightly different than what we talked about on Wednesday. So the first thing that I want to talk about today in particular is what's called the time constant for first order circuits. So on Wednesday, we learned that whenever we have a RC circuit, similar to the one that I'm drawing here, effectively every voltage and current in the RC network will be of the form y of t is equal to y at 0 minus for t less than 0 minus and y at 0 plus times e to the negative t divided by RC for t greater than or equal to 0 plus. And we learned that in an RL circuit, so I'll just draw a simple one of those really quickly. That's going to be VDC. Any voltage or current in the RL network could be expressed as y at 0 minus for t less than 0 naught and y at 0 plus times e to the negative r over L times time for t greater than or equal to 0 plus. Excuse me. Quite obviously, these equations are very, very similar to each other. As a matter of fact, as an electrical engineer, we generally speaking don't care whether it's an RL circuit or an RC circuit. We're just interested in how a first order circuit in general behaves. And the only difference between these two expressions is the coefficient that's being multiplied by time in the exponential function. Everything else is the same. So that coefficient defines the rate of decay for our exponential signal. And we typically give that a fancy name, which is called a time constant. So mathematically, one time constant, tau, is the amount of time it takes a signal to decay to 36.788% of its initial value. Now, you may be thinking to yourself, and it would be a pretty normal thing to think, what is so special about 36.788%? That seems like a very odd number, okay? Why not use decay to 50% so that it would be similar to a half-life in chemistry or something like that? Well, the reason why 36.788% is used is because that is exactly equal to e to the minus 1 power, okay? So I'm going to make, or actually I'm going to draw a plot here. So this could be y of t divided by y at 0 plus. And then this is t here. And so what we should see is some sort of exponential decay. Like so. So at this point along the curve, we're at exactly 1. At somewhere around this point right here, we're out to 1 single time constant. So this looks like whatever e to the minus 1 is, which is 0.36788. Let's call right here to be 2 time constants. And so this value would be e to the minus 2, and we could keep on going for 3 time constants and so on and so forth. I'm going to run out of room on the graph here because my vertical scale is about to just start getting squished. So I'm going to make a table over here on the right. Okay. So we're going to have y of t over y at 0 plus in one column, and then the number of time constants in the second column, like so. I probably should have put this the other way around, but it will be okay. So at 1 tau, we're at e to the minus 1, which is 36.788%. At 2 time constants, or at e to the minus 2, which is 13.5335, so let's call it 13.536%. At 3 time constants, we're at 4.979%. At 4 time constants, we are at e to the minus 4, or 1.832%. And at 5 time constants, we're at e to the minus 5, which is 0.674%. So it takes a little less than 5 time constants for our signal of interest. Doesn't matter whether it's a voltage or a current, doesn't matter whether it's in an RL circuit or an RC circuit. It takes a little less than 5 time constants for our signal of interest to decay to less than 1% of its original value. So in Wednesday's class meeting, I referred to t equals infinity as a long time after our switch had changed states so that our transient condition had died out. In practical terms, 5 time constants is what we consider t is equal to infinity. So it's just however long it takes for our signal to decay to less than 1% of its original value. We call that effectively infinity, and that's where we're back at a DC steady state condition again. If you look at the practice tests and stuff like that, there's definitely going to be a question on some of them that says, how many time constants does it take for a signal to decay to less than 1% of its initial value? The answer is simply 5 time constants. And mathematically, I've shown you here why that is. Okay. So we can modify our equation very slightly to make it work for both RL and RC circuits. So in terms of our time constant, we would have y of t is equal to y at 0 minus for t less than 0 minus, and then y at 0 plus e to the minus t over our time constant tau for t greater than or equal to 0 plus. And so now this generic expression works for both RL and RC circuits, where tau is simply equal to R times C for an RC circuit, and tau is equal to L over R for an RL circuit. Okay. So this is our new generic equation to plug stuff into, expressing things purely in terms of time constants. And then I've defined the time constants for the 2 different types of circuits that we might face over here. So before we move on to the bulk of today's lecture, which is talking about total response, does anybody have any questions regarding time constants or anything like that? All right. So now let's talk about total response. Okay. So in order to talk about the total response, I first want to talk about the natural response. So the natural response of a circuit is what happens when the circuit abruptly loses its excitation sources. So that is exactly what we were looking at on Wednesday. In every problem that we worked, in everything that I derived, a switch was opening up and it was disconnecting either a voltage source and some other resistor network or a current source and some resistor network from either an RL network or an RC network. So everything that we did on Wednesday was what we would call the natural response of a system, or the source-free response of a system, because the source was no longer connected to the energy storage element. The total response actually, before we get to the total response, now let's talk about the forced response. So the forced response of a circuit is what happens when a circuit is excited by a voltage or current source. So this is the forced response because the presence of an excitation source, like a voltage source or a current source, is forcing the energy storage element to behave in a particular way. And then lastly, the natural response sorry, not the natural response, losing my mind today. My apologies. The total response is the combination of the natural and forced responses. So I've described these things with words here. Let me give you guys a circuit as an example that will do a little bit better to help us figure out what's going on. Okay. So let's look at an RC circuit again. So we have our simple DC voltage source. Here is our switch. Here is our resistance. Here is our capacitance. And let's look just in particular at what's going on with our capacitor voltage as a function of time. But this time, instead of saying that our switch is opening at t is equal to 0, let's say that it were to close. Okay. So what would VC at 0 minus be for this particular circuit? Anybody care to offer a suggestion?
0.
0. Would you care to explain your reasoning?
If the switch is open before 0, then the capacitor has no charge.
Exactly right. So we started off in a state where our voltage source was disconnected from our capacitor, so there's no way it can have any charge on it. Perfectly acceptable explanation. Thank you, Joey. What's going on at VC at 0 plus? Anybody care to answer that one?
Equals BDC.
So I disagree, Baylor. The reason why I disagree is because we know that the voltage drop across a capacitor can't change abruptly. So even though the switch is closed, and so that DC supply is in parallel with that resistor and in parallel with that capacitor, it's going to take time for that capacitor voltage to reach VDC. Because if it was 0 volts at 0 minus, it has to continue being 0 volts at 0 plus, right? So we know that always, 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 the capacitor voltage at 0 plus is the same thing it was at 0 minus, which happens to be 0 volts. At t is equal to infinity, however, we would have a voltage of VDC at our capacitor or across our capacitor because we've allowed enough time for the transient condition to die out. So our capacitor is effectively fully charged. And so that's why it has the exact same amount of voltage as the voltage source. So this bit right here is our forced response, okay? Because we have a forcing function, our DC voltage source, that is forcing the capacitor voltage to be non-zero after the transient condition has died out. So this is distinctly different than what we were doing on Wednesday because this voltage source is left in the circuit, and so therefore it's making the capacitor do something it wouldn't normally do or naturally do. Okay. So our total response is simply the sum of the natural response plus the forced response. Okay. So that means that we are going to have our capacitor voltage as a function of time will simply be whatever our natural response was. So that would be VC at 0 minus for t less than 0 minus. And then we would have VC at 0 plus. And I'm going to leave some space here, and you'll see why in a moment. Times e to the negative t over tau plus our forced response, which is VC at infinity for t greater than or equal to 0 plus. Now, can anybody tell me what the problem is here?
There's a resistor.
Nope. So the resistor is what's telling us what's going on with tau. So that in conjunction with whatever the capacitor value is defining our rate of, it used to be decay, but now it's the rate at which our capacitor is charging up. So
Is it the polarity?
it's not the polarity either. So let's look at something really quickly here.
VC
Right?
is 0 in that instance.
Thank you, Leah. That's exactly what the problem is. So what is VC at 0 minus?
0.
0, okay? So if we used this bottommost equation right here, telling us what's going on for t is greater than 0 plus, what happens when we evaluate things at t is equal to 0 plus effectively? We would have VC at 0, which is 0 volts, plus VC at infinity, which is VDC. So according to this equation, our capacitor voltage at t is equal to 0 plus is supposed to be VDC. But we know that can't be true because the capacitor voltage isn't allowed to change abruptly. So we're going to make a very small correction here that'll make things work out right. So instead of just having VC at 0 plus e to the minus t over tau, we're now going to have VC at 0 plus minus VC at infinity. This correction forces the capacitor voltage to be a continuous function in time. So now if we evaluate things at t is equal to 0 plus, we're going to have 0 minus VDC times e to the 0. So that's just going to look like minus VDC plus VDC is equal to 0. And then this term is going to get smaller and smaller and smaller as time progresses, meaning that our voltage signal gradually increases up towards whatever it is at infinity. So if I were to graph this, it would actually look something like this. So here's VC as a function of time. Here's time. So it would start at 0, and then it would gradually increase like so, where this curve right here kind of looks like VDC times 1 minus e to the negative t over tau. And so that's what a charging capacitor is going to look like. More generically, we could say that y of t is now y at 0 minus, for t less than 0 minus, y at 0 plus minus y at infinity, e to the negative t over tau, plus y at infinity for t greater than or equal to 0 plus. So this is our new generic equation. So I want to point something out to you guys really quickly here, because one of the questions that I get asked the most often is, how do I know whether I should use the total response equation or just the natural response equation that we did on Wednesday? And the short answer, and we'll look at this when we look at some example problems, is if there's a voltage or current source left in, use the total response equation. If there aren't any voltage or current sources left in the circuit, use the natural response equation. But realistically, we can just use this one all the time and we'll be correct. Because whenever we have a natural response problem, y at infinity is by definition 0. So it doesn't actually impact anything whatsoever. So if you want to be lazy or things just aren't clicking just yet, if you use this representation for every transient analysis problem, you'll still always get it right. You'll just spend a little bit of time looking at stuff at t is equal to infinity and saying, oh, it's 0, which I already asked you guys to do in the algorithm that we developed on Wednesday. So I've hit you guys with a lot of stuff here. Let's work a couple of example problems in the form of the in-class assignment to kind of sort it out, okay? And if you have any questions about anything, I'd be more than happy to answer them. So for the most part, we don't have to modify the analysis steps that I developed or introduced you guys to on Wednesday practically at all. The only real difference now is instead of finding REQ and CEQ or REQ and LEQ, I'm just going to call that step find the time constant, because that's all we're really doing when we were finding REQ and LEQ or REQ and CEQ. All right, so let's look at this first problem here. In this circuit, we have a switch that has been open for a very long time before it closes at t is equal to 0, okay? So I think that this is going to be a total response problem, because this 12-volt source right here is always connected, okay? So even if the switch opens, the 12-volt source is still connected. With the switch closing, the 12-volt source there is connected, and also this 12-volt source over here is connected. So either way that switch goes, this is going to be a total response problem, not a natural response problem. So let's go through our analysis steps, okay? So step 1 is still going to be to analyze the circuit at t is equal to 0 minus. So at t is equal to 0 minus, that switch is open. So, oh my goodness, I didn't give us much room at all. Let me see if I can add a page here. So edit. And page. Let's just put a blank page here. Okay, so now we have some room. I'm going to move just this statement down. Oh, it's not going to let me do that. Okay, well, that'll be all right. I'm going to redraw my circuit. So we have that 12-volt source. We have the open circuit of our switch. We have a 2-ohm resistor. Our second 12-volt source. We have our 4-ohm resistor. Over here on the right, we have another 2-ohm resistor. This is a voltage drop VR of 0 minus that we're interested in. And then up here, I'm going to have my inductor. What should my inductor look like right now?
Piece of wire.
Exactly right. So because we're at t is equal to 0 minus, it should just look like a piece of wire or a short circuit. So before we get into our analysis, what's going on with the 4-ohm resistor?
It's shorted out.
It's shorted out, absolutely right. So because it was directly in parallel with our inductor, and we replaced our inductor with a short circuit, this 4-ohm resistor right here can completely be ignored. So we're just going to treat it like it doesn't exist. So with that being said, how might we figure out our inductor current at 0 minus and our resistor voltage at 0 minus?
Twelve volts times 4 ohms. I'm sorry, divided by 4 ohms.
So 12 volts divided by 4 ohms. So I agree with that. Would you care to explain how you came up with that?
It's Ohm's law.
Yeah. So we know that there is a total of a 12-volt drop across this 2-ohm resistor, effectively in series with this 2-ohm resistor, because the 4-ohm resistor was bypassed, right? So 12 volts over 2 ohms plus 2 ohms is 12 volts over 4 ohms, or 3 amps. Absolutely correct. What about VR at 0 minus?
Be 3 amps times 2 ohms.
So 3 amps times 2 ohms is 6 volts. Also absolutely correct. Does anyone have any questions, comments, or concerns about the circuit analysis that we did here before we move on to step 2?
So with this problem, we're just using KVL around that right-hand side loop, and we're just ignoring the left-hand side voltage source.
Right. So the left-hand side voltage source isn't really doing anything, or it's not going to contribute any current or anything like that because it's not connected to the circuit, the right half of the circuit, right? So mentioning Kirchhoff's voltage law, that is effectively what we did around this loop, where we know that the current IL at 0 minus is the current that's flowing around this path that I've outlined in purple, because no current is going to flow through the 4-ohm resistor since it's shorted out. So that is a perfectly reasonable way of thinking about things. Any other questions about step one? All right, so let's look at step two. So step two is still to simply analyze the circuit. At t is equal to 0 plus. So at t is equal to 0 plus, our switch is closed. So we've got a 12-volt source. Here we have a 2 ohm resistor in series with a 12-volt source. Here is our 4 ohm resistor. Here's another 2 ohm resistor. This is VR at 0 plus. What should I do with my inductor? So what did we do on Wednesday when we had
It's
an...
part of a DC circuit, so it's shorted out.
So we're at t is equal to 0 plus, which is the beginning of the transient. So we are no longer at DC steady state, which means we should not use our DC equivalent. So what did we do on Wednesday at 0 plus with an inductor?
An open circuit.
I disagree with that.
Did we replace it with a voltage source?
Yeah.
We replaced
Current
it
source.
with current source. So we replace inductors with current sources at t is equal to 0 plus, and we replace capacitors with voltage sources at 0 plus. So I'm going to put a current source here, and we need to make sure that the current is flowing in the same direction as IL was at 0 minus, which was from left to right, and it needs to have the same value as IL at 0 minus. So just to reiterate, we know that the current flowing through an inductor cannot change abruptly. So whatever current was flowing at 0 minus has to be flowing at 0 plus, which is 3 amps. And that's what allows us to treat the inductor like a current source at this particular instant in time. Okay. So how might we go about solving for VR at 0 plus?
It's gonna be the 3 amps times the 2 ohms.
It's going to be current
No, it's
division.
gonna, yeah.
No.
So it isn't going to be 3 amps times 2 ohms, because this 3 amps that's flowing in right here now has an opportunity to split. So some of it might flow this way, some of it's going to flow down. So it's probably not going to be all 3 amps, because there's really no way for us to make that assumption with any valid reasoning.
Back to that point of the current division. So it'd be the 3 amps times the 1/2 over 1/2 plus 1/4.
So I'm not sure about the current division either, because that 2 ohm resistor isn't in parallel with that 4 ohm resistor, right? So if we identify our nodes really quickly here. So we've got this node over here on the right. This node here on the top left. This node here on bottom. And then technically speaking, we also have this purple node right here. So because the 4 ohm resistor is between the blue node and the red node, and the 2 ohm resistor over here is between the red node and the green node, they're not in parallel, so we can't use current division either.
Mesh analysis, and then you'd multiply it by the 2 ohm.
So we could definitely do mesh analysis. I personally would do nodal analysis for a couple of different reasons. Okay. So if we did mesh analysis here, let's just look at things really quickly, right? So we would have a mesh current I1, a mesh current I2 that would be exactly 3 amps, and a mesh current I3. So we would effectively have a 2 equation, 2 unknown system, solve that, and then whatever I3 is times 2 ohms gives us the voltage that we're looking for. There is nothing remotely wrong with that. I want to be really, really clear, okay? But if we did nodal analysis and we chose the bottommost node to be ground, what's the nodal voltage at the blue node?
Twelve volts.
What's the nodal voltage at the purple node?
12 volts.
Also 12.
So the only unknown voltage is the voltage at the red node. So it's actually not even really nodal analysis. It's just KCL at the red node gives us what VR is, because the positive polarity terminal is at the red node and the negative polarity terminal is at ground. So there's nothing wrong with using mesh analysis here, but nodal gives us our answer in literally one step. So that's the one that I'm going to use. Actually, I should have erased that. So we would have VA minus 12 volts over 4 ohms plus VA over 2 ohms minus 3 amps is equal to 0. And we could just solve this for VA. So I'm going to throw that into my numerical solver really quickly. So that's going to look like x minus 12 over 4 plus x over 2 is equal to 3. Calculator is thinking. And I got 8 volts. Do you want to do mesh real quick just to make sure that that's right, or are we good?
No, sir.
Okay.
I saw the KCL at that intersection right there with the 4 ohms and the 2 ohms resistors right there above it, but I didn't know if it would be correct.
Yep. So that is one of the great and also great, in my opinion, awful things, probably in you guys' opinion, is there's always multiple different ways to solve for things. I'm trying to help you guys figure out at least how I think about doing things in the most efficient way possible. So if you suggest something and I'm like, hey, let's maybe look at it this way, I'm not in any way, shape, or form trying to tell you that you're wrong. If you are incorrect, I'll let you know why. But I'm always interested in doing things efficiently. And you guys should be too, just because you only have a fixed amount of time to take your tests. So doing it in the most efficient way possible allows you the most amount of time per problem to work on things. All right. So anybody have any questions about step number 2 before we move on to step number 3? All righty. So step number 3 is to analyze our circuit. at t is equal to infinity. So at t is equal to infinity, our switch is still closed. So we have our 12-volt source connected to a 2-ohm resistor in series with a 12-volt source. Here is our 4-ohm resistor. Over here to the right is our 2-ohm resistor, and we're looking for VR at infinity. And then across the top here, yet again, I have my inductor. What should my inductor look like at t is equal to infinity?
Piece of wire again.
Exactly right, Joey. Thank you. And here is our current IL at infinity. So once again, our 4-ohm resistor is shorted out, so we can just ignore it. So anybody have any thoughts on how we might solve for either IL at infinity or VR at infinity?
Nodal.
Okay, so I'm going to identify my nodes. So there's one node. Here's another node. And then here's my last node. So before I commit to doing nodal, I want to make an observation. The 12-volt source on the left is connected between the red node on top and the blue node on bottom. And our 2-ohm resistor on the right is connected between the red node on top and the blue node on bottom. What does that mean?
It's just 12 volts.
Exactly right. So the 12-volt source on the left is in parallel with the 2-ohm resistor on the right, which means VR at infinity is just 12 volts. Now, let's make another quick observation here. So let me do this in purple. So this current right here is IL at infinity. I'm going to drop the at infinity just because it's going to be bothersome. We know that no current branches off and flows to the left through the 4-ohm resistor because it's shorted out. So all of our inductor current, IL, has to flow down through the 2-ohm resistor. So how might we solve for IL?
It's just 6 amps.
Exactly right. So just 12 volts over 2 ohms is equal to 6 amps. So we could have absolutely, and I know nobody suggested this, but we could have thrown mesh at this or thrown like a full-on nodal analysis or something like that at this. But that would have been overkill because just taking a moment to look at what's going on got us actually both of our answers very easily. Okay. All right. Any questions about step number 3? Okay. So now let's look at step number 4. So This step is effectively going to have a new name, but we're not doing anything different than we did previously, right? So we're going to call this now determine tau during the transient. Since this is an RL circuit, we're going to have an LEQ, and then we're also going to find REQ. So let's scroll up here. What's LEQ?
2 Henrys.
2 Henrys, right? Only one inductor, so nothing particularly difficult about that. Now I'm going to redraw my circuit during the transient condition. So I have a 12-volt source here, 2 ohm resistor, 12-volt source here, 4 ohm resistor, 2 ohm resistor. Up here's my inductor, right? When I'm finding REQ, I'm always doing it with respect to the energy storage element, which means I take my inductor out and I'm going to look in through those terminals to find REQ. And I also need to be looking at a dead network, which means I turn off my 12-volt sources by replacing them with short circuits. Sorry. Right. No. I do not want to use OneNote. I want to erase this. Sorry about that. I don't know what the heck my computer was doing. So I'm going to take a moment here and just identify nodes really quickly. So based on the nodes that I have identified, what do you guys think my equivalent resistance is going to be?
2 ohms in parallel with the 4.
Exactly right. So this 2 ohm resistor right here is shorted out, so it doesn't contribute anything. And both the 4 ohm resistor and the 2 ohm resistor that are left are between the red and the blue node, so they're in parallel. So to me, that looks like 4 times 2 over 4 plus 2. So that would be 8 over 6 or 4/3 of an ohm. Goodness. While we're at it, let's go ahead and calculate tau. So tau is LEQ over REQ. So that's going to be 2 Henrys divided by 4/3 of an ohm, which would be 6/4 or 3/2 of a second. And you'll see why I'm doing this in a moment. The inverse of tau is then going to be 2/3 per second. So lastly, actually, before we move on with step 5, does anybody have any questions about what we did in step 4? So lastly, we're just going to plug stuff in to our generic equation. So our generic equation, just to remind you all, is y of t is equal to y at 0 minus for t less than 0 minus, and y at 0 plus minus y at infinity, e to the negative t over tau plus y at infinity for t greater than or equal to 0 plus. So let's start with IL of t. So what was IL at 0 minus? I can scroll up if you need me to.
3 amps.
So 3 amps, okay. What was IL at 0 plus?
Also 3 amps.
Okay, so we have 3 amps minus what was IL at infinity.
6.
Okay, so we have 3 minus 6, so that's going to be -3. E to the minus, so T over tau is the same thing as T times the inverse of tau, so I'm just going to put -2/3 T. So that's why I bother doing that tau to the -1. It just tells me what coefficient to multiply T by. Plus 6 amps for T greater than or equal to 0 plus. And then we have VR of T. So what was VR at 0 minus?
6 volts.
6 volts. What was VR at 0 plus?
8 volts.
Okay. So what was VR at infinity? Looks like 12. So 8 minus 12 is -4. E to the minus 2/3 T plus 12 volts for T is greater than or equal to 0 plus. So this process for determining the total response of a circuit is extremely similar to what we were doing on Wednesday. All right, does anybody have any more questions about this particular problem before we move on to number 2? And I want to be really clear here. If something is not making sense, please, please, please ask me and I'd be happy to explain. All righty. So here we have problem number 2. We have now a circuit containing a capacitor. The switch has been closed for a very long time before opening at t is equal to 0. And hopefully we can all see that the switch over here opening up does not in any way, shape, or form disconnect this 6 milliamp source here in the bottom middle. So this is also a total response problem. All right. So let's start with step number 1. Analyze at t is equal to 0 minus. So let me redraw my circuit here. The switch was closed. I have a capacitor over the top. What should I do with my capacitor?
It's an open circuit.
Exactly right. Thank you, Austin. Okay. So we are looking for IR at 0 minus and VC at 0 minus. Anyone have any thoughts on how we might go about solving for either of those two quantities?
Do a current division for IR and then just do IR times 10 kilo ohm. Or where's, never mind.
So current division, I am definitely on board with. So let's use that to find IR at 0 minus. Okay. So IR at 0 minus. So we're going to have 6 milliamps. And then the resistive path that we're finding the current through has this 2 kilo ohm resistor effectively in series with this 10 kilo ohm resistor. So that's going to look like 1 over 10K plus 2K divided by 1 over 10K plus 2K plus 1 over 4 kilo ohms. So let's see, that's 1/12 over 1/12 plus 3/12. So that's 1/4. So 6/4 is 1.5 milliamps, or 3/2 of a milliamp. Okay. Anybody have any questions, comments, or concerns about how I applied current division there, or maybe why I can apply current division there? All right. So let's talk about figuring out that voltage. So figuring out this voltage is actually a little bit harder. Okay. So to me, because you know what, Baylor, I may have told you that you were incorrect, but I am the one who is incorrect. I have been doing it a much more difficult way than I needed to for the past 4 years. So thank you for your suggestion. Sorry. So Baylor a moment ago said that VC at 0 plus should just be 10 kilo ohms times IR at 0 minus, which was 3/2 of a milliamp, which comes out to be 15 volts. So let me explain to you how I've been doing it, and let me also explain to you why Baylor was very correct, and it's a much easier way to do it his way. So what I had been doing was saying that VC at 0 minus was the voltage drop across this 2 kilo ohm resistor, which I'm going to call V2K, plus the voltage drop across this 4 kilo ohm resistor. And so I found both of those voltages effectively by using current division to find the current that was flowing through them, and then using Ohm's law, right? So that's what I was doing. There's nothing particularly wrong with that, but it is actually much harder than what Baylor suggested. So if we identify our nodes here, so here's one node. And here's another node here on bottom, and then we've got the node in the middle, but that doesn't really matter. We can see that even though it doesn't look like it, our capacitor is actually in parallel with that 10 kilo ohm resistor. So the current flowing through the 10 kilo ohm resistor times the 10 kilo ohm resistor is indeed the voltage drop across the capacitor. So thank you very much for that suggestion, Baylor. You are absolutely correct, and I never noticed it for literally years. So great job. You have improved the efficiency.
Good job, Bebe.
All right. So does anybody have any questions, comments, or concerns here about step number 1? Okay, so let's go on to step number 2.
Hey, Dr. Hartman, I have a question.
Absolutely. Shay, what's up?
So is it wrong to think of it as just a KVL around the outside loop?
That is exactly another way to think about it that would give you the exact same result. 100% correct.
Okay, thank you.
Yep, so what Shay was suggesting there is if we did KVL around the outside loop, let me label the voltage drop across this resistor right here. Let me just call it VR for a moment. So if we did KVL around the outside loop like so, we would have negative VR plus VC at 0 minus is equal to 0, since everything along this part of the path right here is just a short circuit. And that gives us the exact same result. So also an absolutely reasonable way to do it. So thank you for that suggestion, Shay. Any other questions or anything about step one? Okay, step two. So now we're analyzing our circuit at 0 plus. And at t is equal to 0 plus, our switch is opened up. Okay. So this is what our circuit is going to look like. Here's our 2 kilo ohm resistor, our 6 milliamp source, our 10 kilo ohm resistor through which we have a current of IR at 0 plus flowing. Here's our 4 kilo ohm resistor. Our switch was opened over here, so I'm going to just take that. So what do I need to do with my capacitor?
Replace it with a voltage source.
Replace it with a voltage source having the same polarity as VC at 0 minus, as well as the same value. So we're going to put a 15-volt source, positive polarity on the left, negative polarity on the right. And just really quickly here, I'm going to make a note that VC at 0 plus must be the same as VC at 0 minus is 15 volts. So now we need to figure out what IR at 0 plus is. Anyone have any thoughts?
Well, we only have two meshes here, so as much as we like to always try mesh analysis, I think it might actually be a good option here.
I was gonna say nodal.
Might I suggest neither? So let me explain what I mean. How much current is flowing through the branch that I just denoted with that arrow?
0.
0 amps. So that means that whatever current is flowing along here, which is IR, has to turn up and flow through the 6 milliamp source. So what's IR?
6 milliamps.
There we go. So we could have gotten that result using nodal or mesh, but KCL at the bottom node got us there faster.
What goes in must come out.
Exactly right. So any questions about our analysis for step number 2? Okie dokie. So let me add another page to this thing. And now we're going to look at step number 3, which is just figuring out what's going on at infinity. So at t is equal to infinity, we're going to have our 2 kilo ohm resistor here, our 10 kilo ohm resistor here. Here's IR at infinity. Here's our 6 milliamp source, our open switch, our 4 kilo ohm resistor. And then what is my capacitor going to look like at t is equal to infinity?
Open circuit.
Open circuit. Thank you, Joey. Plus minus VC at infinity. So let's do the easy one first. What's IR at infinity?
Is 6 milliamps again?
6 milliamps. Absolutely. VC at infinity is a little harder. Anybody have any thoughts?
It seems to be in parallel with the 2 kilo ohm.
So I disagree with that. So let me identify some nodes here. So we've got this red node here in the top left. Let's put a blue node here in the middle. Purplish node here on the top right. And then a green node here on the bottom. So it's not in parallel with the 2 kilo ohm resistor because the 2 kilo ohm resistor is between the red and the blue node, and the 4K is between the purple and the blue node. So there are some observations that we can make that'll make this a little easier to figure out. Okay. So how much current is flowing through this path?
What if we
0.
0. Because we have an open circuit up here. We also have an open circuit down here. So there's no current flowing through the 4 kilo ohm resistor at all. So what's the voltage drop across the 4 kilo ohm resistor?
Also 0.
Yep. So the 4 kilo ohm resistor doesn't really do anything. So we could get rid of it and just treat it like it was a short circuit because there's no voltage drop across it. So now we can see that the capacitor, and I may have misunderstood, maybe not, things a moment ago, and if I did, I apologize, but it seems like the capacitor is in parallel with the 2 kilo ohm resistor. So if we can figure out what the voltage drop across the 2 kilo ohm resistor is, then we know the capacitor voltage. Anybody have any thoughts on what the voltage drop across the 2 kilo ohm resistor is?
12 volts.
So 12 volts, because all 6 milliamps is going to flow through it. But what's the polarity? So we're going to have 12 volts. I agree with that. Positive polarity on the left or positive polarity on the right?
On the right.
So how does that polarity compare to the voltage drop across the capacitor?
negative?
Negative. So VC at infinity is negative 12 volts. And for whoever said in parallel with the 2 kilo ohm resistor, I apologize if I misunderstood what you meant by that. So. All right. Does anybody have any questions or comments about our analysis here at t is equal to infinity? Okay. So step number 4 is to, sorry, it is not to analyze. It is to determine tau during the transient. So I'm going to redraw my circuit really quickly. So I have my capacitor across the top, 2 kilo ohms, 4 kilo ohms, 6 milliamps, 10 kilo ohms, like so. I take my capacitor out, leaving behind an open circuited set of terminals. So here's REQ. And I turn off my current source, which means I replace it with an open circuit. So what is REQ?
Uh, 10 in parallel with 2 plus 4.
So
Or no, open, never mind. It's just 2 plus 4.
this 2 plus 4, so just 6 kilo ohms. Absolutely. And then CEQ was, go all the way back here, 150 microfarad. From this, tau is 150 times 10 to the minus 6 times 6 times 10 to the positive 3. So 0.15 seconds. And the inverse of tau is then 20 over 3 per second. Anybody have any questions or concerns about step number 4? All right. So step number 5 is literally just plug stuff in. So our generic equation is y at 0 minus for t less than 0 minus. Sorry about that. Y at 0 plus minus y at infinity for e to the negative t over tau plus y at infinity for t greater than or equal to 0 plus. So for our capacitor voltage, let me just scroll up here, 15 volts. So that's going to look like 15 volts for t less than 0 minus, and then 15 minus negative 12 is 27 e to the negative 23rds t minus 12 volts. And then IR as a function of time. So that's going to be 1.5 milliamps and then 6 milliamps. So 3/2 of a milliamp for t less than 0 minus. And then, so let me do this out a little bit here so you'll see what's going on. So we had 6 milliamps at 0 plus minus 6 milliamps at infinity. So that's just going to look like 0 e to the blah, blah, blah. So it's really just going to be 6 milliamps DC for t greater than 0 plus. But it still fits the exponential model. It's just the exponential is multiplied by a factor of 0. All right, so that is really all that I wanted to talk about for today. I am more than happy to answer any questions that you guys might have about any homeworks or anything. Just as a heads up, all I have planned for Monday's class meeting is to just work out the in-class assignment. It's a little bit harder than what we did today, but not by much. I say it's a little bit harder because it's the first one that has more than one capacitor or inductor in it. After I do that, we can just start reviewing for the test. Then next Wednesday's class meeting is also dedicated to test review, and then Friday is nominally the day for the test. So, what do you guys want to do for the next 20 minutes or so?
Dr. Hartman.
Yes, sir.
So we got 27e to the negative 20 over 3t.
Mm-hmm.
I just want to make sure, because either we're wrong or the answer's wrong, but in the answer it says 27e to the negative 10 over 9t.
So perhaps we calculated our time constant incorrectly. So let's look at some things here really quickly, right? I'm just gonna identify my nodes. And it's always a possibility I just put it into my calculator wrong as well.
Yeah, I got 0.9 for the time constant.
Okay. So definitely 2 kilo ohms in series with 4 kilo ohms. So I may have just put stuff in my calculator incorrectly. So 150, because tau should just be RC, right? So 6 times 10 to the 3. Oh, I don't think I put the 6. That's probably what it is. 150 times 10 to the minus 6, 0.9. Take the inverse of that, which would just be 10 over 9. It's just me using my calculator poorly. Thank you for that correction, though. Yep. Okay. I just typed it into my calculator wrong. Sorry about that. Any other questions or comments or concerns? All right. Well, I hope you guys have a great rest of your afternoon, and I will see you on Monday. Austin, if you have a moment, we can switch over to that other Zoom meeting, and I can finally answer whatever your question was.
Yes, sir, sure.
Yeah, and sorry about making you wait for 3 days.
No problem.
All right. Thank you, guys. I'll see you on Monday.